Hello, this is Doug Leifer, and I am going to present to you Problems from Mechanics of Materials by R.C. Hibbeler. This is the 10th edition from 2018, and the problems that you will see in this video and this series of videos are all solved in Excel. And so I feel that after teaching this course for many years, Excel is a great tool to perform optimization, computations, and to solve for unknowns in the course. So we're going to start with chapter 1, and we're going to look at concepts of stress in this chapter. So the first problem we will do is a very straightforward problem. And this is example 1.1. Determine the resultant internal loadings acting on the cross section of the beam. It's cantilevered at point C. So you can see the beam in figure 1.4. So what we're going to do is set up an Excel sheet, and we type in the given values. For the distance from the cantilevered wall to C, A to C is 3 meters, and that's just typed in as a 3. The distance from point C to the end at B is 6 meters. The length of the span is just the sum of the two, 3 plus 6. And we like to make this interactive so we can add any numbers or change any values as we wish. And the distributed load at B is 0 newtons per meter, and that increases linearly along the beam up to the cantilevered wall to 270 newtons per meter at point A, and that's triangular. So by proportion, we want to know what the distributed load would be at point C. So we can just take 270 over the whole length, which is 9, is equal to W, which is the unknown, over 6. And that's achieved by just calculating 6/9 of 270. So we use 270, which is cell D25, times 6 over 9, which is just the length of C to B divided by the total length of the span. So it's 180. So then we cut the beam at C, and that would be from point B, where the distributed load starts. That's a distance of 6 meters, so we type in 6. So the load then is going to be the 180, okay, times 6, which is the distance, divided by 2, since it's triangular. So we're replacing the distributed load from B to C, which is triangular, increasing from 0 to 180 now that we've calculated, and we're going to replace it with a point load of 540, and that's just simply 180 times 6 divided by 2, since it's a triangular load. And the location of that is at the centroid of that triangle, so it's 2/3 of the distance from B to C, so that would be 4 meters. So I just multiplied C to B, which is this cell, by 2/3. And there we have it. So everything's interactive. If we change point C to a different point, for example, we could easily just do that in the sheet. So now we sum the forces. The sum of the forces in the x direction, we look at the free body diagram in figure B here on the upper right. It's just like minus n sub c is equal to 0. So that means n sub c is equal to 0 newtons. There's no normal force. And that our summation of forces in the y direction, we have v sub c upward, minus 540 downward. That's the point load that was replaced with the distributed load that was replaced with the point load. So that's vc minus 540 is 0. These are all equilibrium equations. And so vc is 540. Just move it to the other side of the equal sign. And then lastly, the moment. We're going to take the moment. So the moment at C is a negative moment, as you see here. By convention, it's clockwise, so that's negative. And then minus 1080. Where do we get that? We take 540, the point load that replaced the distributed load at the centroidal distance of that short triangle, and then we multiply it by its arm, its moment arm of 2, so 540 times 2. But that's going to also create a clockwise moment, so that's also negative. So minus mc minus 1080 is equal to 0. So that means the moment at C is minus 1080. So it's opposite to the direction shown in the diagram. And that's the solution to example 1-1. So let's go on to one more problem. in this chapter. And this is example 1.6. It says the 80 kilogram lamp is supported by two rods, and they're anchored to the wall at A and C. So there are rods AB and BC, and they have different diameters and different angular configurations to keep this lamp in equilibrium. So here's a free body diagram on the right in figure B. And you can see the angles and the configuration of the triangle here, which looks like a 3, 4, 5 triangle of FBC B to X. And then we have our weight of the hanging lamp converted to newtons by multiplying the mass in kilograms times gravity. So let's fill in the sheet. The mass is 80, gravity is 9.81. The weight is just simply the product of those two cells. The diameter of rod AB is 10 millimeters, that's given. So we're going to convert it to meters by dividing it by 1,000. And the diameter of rod BC is 8 millimeters given, and we're going to divide that by 1,000 to get to meters. So then we're going to calculate the areas, cross-sectional areas of each rod. We need that in order to get the normal stress. So that's just simply going to be pi d squared over 4, and we use the meter diameter cell to do that. So pi, which is just pi, and the open and close parentheses, times the diameter in meters, that cell, and it's that's squared, and then the whole product is divided by 4. Same thing for area of BC. So we have our areas in square meters. We do that for consistency with units. FBA angle is given. FBC angle is not given. Where did we get the 36.87? Well, we can say that at the angle that's inside here, which would be angle FBC-BX in that triangle, if we want to take the tangent of that angle, it would be the opposite over the adjacent. That's 3 over 4, you can see from the triangle. So if we take the arc tangent of 3 over 4, here we've done that. We had to convert to degrees and then take the atan arc tangent of 3/4. We get the angle rounded to 2 decimal places, 4 significant digits. So then we go over to our summation of forces. The sum of the, since this is in equilibrium, the sum of the F sub x forces is 0. So what are the x forces? Well, you have minus FBA sub x, and that's going to point to the left, so it's negative, plus FBC sub x, that's going to point to the right along the x-axis, so that's positive, equals 0. Then you sum the y directional forces. You'll have FBAY, which will point straight up along the y-axis, is positive, plus FBCY, which points straight up along the y-axis, minus the weight of the lamp, which is 784.8 newtons, equals 0. So this could be done using a number of approaches, elimination, for example, or it could be done using matrix operations and inverse matrices. But we're going to do it with Excel solver because we have two unknowns here. FBA and FBC, we don't know what they are. And in order to calculate the average normal stress on each rod, we need those values in newtons because once we have them, we're going to divide by the cross-sectional areas in square meters to come up with the average normal stress in pascals. So what I've done is I've put in a starter value of 1 for each of those unknowns. Now you would not want to use 0 in this sheet, and you could probably see why. So let's just keep it at 1. It's never good to use 0 as a starter value, so we'll keep it as a positive integer. So then we want to actually sum the forces in the x direction based on those 1 starter values. So that would be, here's the code or the Excel equations. It's minus 07 times the cosine of the angle from K14, which is 60 degrees, but you have to put it into degrees. So that is going to give us, if you just sum this, it'll give us 0.3. Well, it should be 0, but it's not because these values are randomly assigned as starter values. And we need to get to the right number so that the sum of the forces in the x direction is 0. So this is probably one of the more important calculations, is that you're actually calculating what the sum of the forces in the x direction should be. So you'd have minus FBA cosine of 60, and then plus FBC cosine of 36.87, and those together are going to equal 0 if you add those together. But they don't. They equal 0.3 right now, which is fine. And then the sum of the forces in the y direction, you'll have this formula. And this formula just simply says, okay, FBA, whatever it is here, it's 1 times the sine of 60, and then plus FBC, whatever it is, here it's 1 times the sine of 36.87, right, or the cosine of 53.13. So that, and then minus 784.8. Well, that ends up being a non-zero number as well. So it should be 0 because we've already previously shown due to equilibrium conditions. So I drew in these arrows for a little color coding here. So then now we need to use Solver. So if we go to Solver, we'll go into Data and then Solver. This is an add-in, so you'll have to add it. Now, if you haven't added it, maybe it's a good time to show how to add it. File, Options at the bottom, and then Add-ins over here, and then Manage the Add-ins, Go, and then Solver should be checked, just Solver. And then click OK. And I already have it, so I don't need to reinstall it. So I'm going to Solver. I have a pop-up window. It says set the objective. Well, I want the objective, which here is 010, and it should be 0. It's 0.3, so I want to set it to 0, to a value of 0, by changing both FBA and FBC. So those are in cells 07 and 08. So I got 2. Subject to the constraints that FY summation is also 0. So that would be 011. So that's important. So I've added that in. And then we want to say make unconstrained variables non-negative. Then we just click Solve. And up comes another pop-up window, and it says Keep Solver Solution. And we click OK. And here's our answer. So FBA is actually 632.4, roughly, newtons. FBC is about 395.2 newtons. And if we divide those by their respective cross-sectional areas, we get 8.05 megapascals for sigma FBA, the average normal stress in FBA, and then 7.86 megapascals for the average normal stress in FBC. So let's just show you that one more time before we wrap this up. The key is that F sub x and F sub y have to be calculated based on these starter values using the correct trig functions and respecting the need to make sure that you're actually taking the cosine in degrees. Here I used radians to assure that it is the cosine indeed. And previously I used the degrees for an arc cosine function. So it's important to understand when to use radians or degrees in the formulas. Here I used the radians, okay? So then we know that these should both be 0, but they're not. So we're going to use Solver, and we're setting 010, which is this FX cell, to 0 by changing FBA and FBC. Those are these cells 07 and 08, subject to the constraint that 011, the F sub y force, is also 0, and then we click Solve, and we get our results.